In the beginning there was only the void, and a singularity of infinite density. Then, in a moment science has named the Big Bang, around 13.8 billion years ago, the universe exploded into existence. The first fractions of a second were so intense that no form of matter could remain stable. Everything was pure energy. But as the cosmos expanded and cooled, fundamental particles began to emerge: quarks, electrons, and positrons. These particles soon combined into protons and neutrons, forming the first rudimentary atoms. In this scorching primordial environment, the lightest elements in nature were born: hydrogen, helium, and trace amounts of lithium. These were the initial building blocks, the basic ingredients of all visible matter in the universe. During the first 300,000 years, the universe remained an incandescent plasma, where light and matter could not separate. But when temperatures dropped low enough for electrons to bind to nuclei, the first stable atoms were formed. This event, known as recombination, allowed light to travel freely, and that ancient light can still be detected today as the cosmic microwave background radiation. Even then, the universe remained dark, cold, and silent for millions of years. Only hydrogen, helium, and a touch of lithium filled the cosmic void. All other elements, from metals to life itself, did not yet exist. The universe was literally a vast, inert cloud of light gases, awaiting gravitational collapse. The birth of stars marked the great cosmic turning point. When clouds of hydrogen became dense enough for gravity to dominate, they began collapsing under their own weight. Heat increased until it reached millions of degrees Celsius, triggering nuclear fusion. In this process, hydrogen atoms fused to form helium, releasing colossal amounts of energy. The first stars were born, giant, bright, and short-lived, becoming the true forges of the universe. In their cores, new elements began to form: carbon, oxygen, nitrogen, and many more. The stellar cycle began shaping the cosmos. When these massive stars exploded as supernovae, they ejected these new elements into space, seeding the universe with the raw materials for planets, life, and technology. Supernovae are events of unimaginable violence, but also of profound creation. In them, heavier elements like iron, nickel, and even gold are produced. During these colossal explosions, pressure and temperature reach such extreme levels that heavy atoms can form in mere seconds. Every atom of iron in your blood, every particle of calcium in your bones, was forged in the heart of a dying star. For billions of years, the universe has been recycled through these events. Stars are born, live, explode, and spread their elements. New stars form from this enriched matter. Around them, planets emerge, and on at least one of these planets, life arose with the ability to understand the origin of the elements and build a periodic table to organize them. Thus, the story of the elements begins long before the table we know today. It begins with the birth of time, of light, and of stars. To understand the origin of the elements is to understand that everything we touch, the water, the air, the metals, even our own bodies, is made of stardust. We are composed of the oldest atoms in the universe, rearranged into complex and momentarily conscious forms. The periodic table, which will be our guide from now on, is more than a scientific tool. It is a condensed map of cosmic history. Each square, each symbol, carries billions of years of evolution, death, and rebirth. And from this knowledge, humanity began to master the matter around it. For centuries, alchemists and early chemists studied the nature of matter as if they were trying to decipher a secret code of creation. Each known element was an isolated discovery, almost magical, surrounded by mysteries and peculiar properties. Sulfur burned with an unmistakable odor, mercury flowed like a liquid mirror, and gold resisted time as if it were eternal. But there was no order. Each substance seemed to belong to its own separate universe, with no apparent relation to the others. Chemical knowledge was growing in quantity, but not in structure. It was like having puzzle pieces without knowing what picture they formed. A system was missing. A logic was needed to reveal the invisible connections between elements. Then, in the 19th century, an idea emerged that would forever change science, organizing the known elements based on their properties and atomic masses. This revolution did not come suddenly, but almost inevitably, as if accumulated knowledge itself was demanding structure. Several scientists tried to classify the elements, noticing patterns in their chemical properties. Some proposed triads, others designed tables with 8-element rows, but it was the Russian chemist Dmitry Mendeleev who saw the full picture clearly. In 1869, he published the first version of the periodic table of elements. Mendeleev's most remarkable achievement wasn't merely grouping the known elements, it was leaving gaps. He predicted, based on the regularities of the system, the existence of yet undiscovered elements like germanium and scandium, describing their properties with precision before they were ever isolated in a lab. Mendeleev didn't just organize matter, he uncovered a hidden language embedded in the structure of the universe. The brilliance of the periodic table lies in its periodicity, the repetition of similar properties in recurring cycles of elements. With the advance of atomic physics in the 20th century, scientists discovered that this periodicity stems directly from the structure of atoms, more specifically from the configuration of their electrons. Elements are not just different substances. They are variations of the same underlying pattern, defined by the number of protons in their nuclei and the way their electrons are distributed in shells around them. The vertical groups of the table, such as the halogens or noble gases, share properties because they have similar electronic configurations. The horizontal periods, in turn, reveal a systematic progression of atomic number and electron shells. Thus, the periodic table came to be seen not just as a chemical tool, but as a mathematical and physical expression of the structure of matter. The organization of the elements brought immeasurable practical consequences. It enabled the prediction of chemical reactions based on atomic positions. It led to the development of metal alloys, medications, fertilizers, fuels, and nuclear technologies. The periodic table was the basis for the discovery of transition metals, which are vital to industry. It explained the behavior of noble gases, essential for lighting and cryogenics. Every scientific discovery from then on relied on a deeper and more systematic understanding of the elements. The table became the alphabet of matter, each symbol a verb of transformation, each column a chemical rhyme, each row a rhythm of atomic reality. And even today, with 118 confirmed elements, the table remains alive and expanding. New elements continue to be synthesized in particle accelerators, revealing both the reach and the limits of matter. With each new addition, the map becomes more complete, but the wonder remains unchanged. The periodic table is a bridge between the atomic microcosm and the macrocosm of civilizations. It is used by engineers building satellites, by doctors treating cancer, by agronomists fertilizing soil, and by chefs mastering the flavors of cooking. It appears on a computer chip and in the fusion reactions that power the sun. Organizing the elements was more than a scientific triumph. It was a way of translating the universe so that the human mind could understand it, manipulate it, and recreate it. When the universe was born, in the rapid expansion of the Big Bang, two elements emerged before all others, hydrogen and helium. Together, they still make up over 99% of the visible matter in the cosmos. Hydrogen, with only one proton and one electron, is the simplest and most abundant atom of all. Helium, with 2 protons, 2 neutrons, and 2 electrons, is the second lightest element, but also one of the most stable and inert in nature. These two cosmic siblings are not merely ancient particles, they are the pillars of existence. Everything we see around us, from interstellar dust to living beings, began with them. Before there was carbon for life, iron for blood, or oxygen to breathe, there was hydrogen and helium drifting through space, silently filling the void with their fundamental presence. Hydrogen, in its simplicity, is also the essential fuel of the universe. It is the raw material of stars. When immense clouds of hydrogen collapse under their own gravity, atoms begin to fuse in their cores, releasing colossal amounts of energy in the form of light and heat. That is how a star is born. The fusion of hydrogen into helium is the engine of stellar life. In the Sun, every second, around 600 million tons of hydrogen are converted into helium, and this conversion releases enough energy to heat the Earth and illuminate the entire solar system. Without hydrogen, the universe would be dark and cold, and without that light, life as we know it could never have formed. Hydrogen is, therefore, the primordial fire, an almost invisible substance that sustains entire galaxies with its continuous glow. Helium, on the other hand, is a silent jewel among the elements. Extremely stable and nearly inert, It does not easily bond with other atoms. It is the first of the so-called noble gases, those that prefer chemical solitude. On Earth, helium is rare, though essential. It is used to cool superconducting magnets in MRI machines, to fill balloons and airships due to being lighter than air, and in extreme conditions, it can even behave as a superfluid, a substance that defies classical laws of physics. But its origin is stellar. Terrestrial helium is formed mainly by the radioactive decay of heavy elements underground, and its natural supply is limited. Every time we use it, a portion escapes irreversibly into space. A cosmic resource, essential and finite. The beauty of the first two elements of the periodic table lies in their duality. Hydrogen is active, explosive, vital. Helium is passive, silent, elegant. One represents the engine of the universe, the other its stability. When combined in extreme environments, such as in the depths of gas giants or in the interiors of massive stars, they create phenomena as colossal as they are invisible to the human eye. They are the first words in the language of matter, and even in biology, hydrogen plays a vital role. It is in the water we drink, in the DNA molecules that carry our genetic heritage, in fatty acids, in proteins, in life. Everything begins with the atom of a single proton. The study of these elements is not merely theoretical. Hydrogen has long been seen as a promise of clean energy. Hydrogen fuel cells, for instance, offer an alternative to petroleum, releasing only water vapor as a byproduct. Helium, even in its limited quantities, is irreplaceable in many scientific and technological applications. They are ancient, simple, and small, yet they are at the center of modern innovation. From the beginning of time to the laboratories of the future, hydrogen and helium show how even the humblest elements can hold the key to understanding and transforming the world. Among the more than 100 known elements in the periodic table, few hold the prestige and prominence of carbon. Although it does not shine like gold, conduct electricity like copper, or possess the exotic magnetism of uranium, carbon occupies a singular place. It is the structural foundation of all life as we know it. Every cell, every tissue, every molecule of DNA, protein, hormone, or fat carries at its core intricately connected carbon atoms. This happens because carbon has an almost magical ability. It can bond with other carbon atoms in chains, rings, and highly stable three-dimensional structures. This capacity to form multiple, long, and branched bonds allows for the creation of an endless variety of compounds. Thanks to this trait, carbon is more than just a chemical element. It is a molecular architect. Carbon is also extraordinarily abundant and recyclable. It exists in the atmosphere, in the soil, in the oceans, and within living organisms. It is present in the carbon dioxide we exhale, in the coal that burns in fireplaces, in the petroleum that powers vehicles, in the diamond of a ring, and in the graphite of a pencil. Its most well-known pure forms, like graphite, diamond, and fullerene, show how a single element can take on radically different physical structures. In diamond, carbon atoms are arranged in an extremely rigid three-dimensional network, creating the hardest known natural material. In graphite, atoms are aligned in layers that slide easily over one another, making it soft and lubricating. In fullerene, they form microscopic spheres or tubes with even more astonishing electrical and structural properties. This variety demonstrates how carbon constantly reinvents itself. From a biochemical perspective, carbon is the foundation of all vital macromolecules, proteins that build muscles and tissues, nucleic acids that store genetic information, carbohydrates that provide energy, and lipids that form cell membranes. All are organic compounds based on carbon. This element offers the stability necessary for life and, simultaneously, the flexibility required for evolution. That is why scientists searching for extraterrestrial life often start with the hypothesis that, if life exists elsewhere, it is likely carbon-based as well. Although some theorists consider silicon a viable alternative, no other element provides the same combination of strength, variety, and ability to form complex bonds at life-compatible temperatures. Beyond biology, carbon has revolutionized technology. The emergence of carbon nanotubes and graphene, a sheet of carbon just one atom thick, has promised materials stronger than steel, lighter than aluminum, and more electrically conductive than copper. These materials are being studied for use in electronics, medicine, energy, and even the construction of space elevators. At the same time, controlling carbon dioxide emissions has become the greatest climate challenge of our era. The carbon cycle, the way it moves through the atmosphere, oceans, living beings, and soil, is one of the most delicate and interconnected systems on the planet. Any imbalance in this cycle can cause profound impacts such as global warming, ocean acidification, and disruptions in ecosystems. Carbon, therefore, is both the spark of life and the measure of civilization. It represents the connection between being and doing, between nature and technology. From the first unicellular organism to the machines now exploring other planets, carbon has been the guiding thread of complexity. It is invisible, silent, yet omnipresent. It is in our blood, in our words, in our memories, and in our inventions. And no matter how far the future takes us into new frontiers of science, it is almost certain we will continue returning to carbon as a starting point, as the element that not only builds, but sustains the very concept of life. It is all around us, fills our lungs with every breath and makes up most of Earth's atmosphere, yet it goes unnoticed. Nitrogen represents about 78% of the air we breathe, and still, almost no one thinks about it. It has no smell, taste, color, or sound. It doesn't burn, it doesn't feed fire, and it doesn't keep us alive directly like oxygen does. And yet, without it, there would be no DNA, no proteins, no muscles, no green leaves or fields of wheat. Nitrogen is the invisible essence of life. Its silence is not absence but balance. It is the backdrop upon which respiration, photosynthesis, and metabolism unfold, stable, calm, and essential. In nature, nitrogen exists in molecular form, N2. This form is extremely stable due to the triple bond between the two atoms, making it chemically inert under normal atmospheric conditions. For this reason, although it is abundant in the air, most living organisms cannot use it directly. To become biologically available, nitrogen must be transformed into more reactive forms, such as ammonium, NH4+, or nitrate, NO3. This process is carried out by a select group of bacteria in the soil or associated with the roots of leguminous plants. This is known as the nitrogen cycle, a constant exchange system involving microorganisms, plants, animals, and the air itself. Without this cycle, life as we know it would collapse. Nitrogen's impact became even more evident during the agricultural revolution of the 20th century, when scientists Fritz Haber and Carl Bosch developed an industrial method to fix atmospheric nitrogen and convert it into ammonia, known as the Haber-Bosch synthesis. A new era began for humanity. For the first time, it was possible to manufacture nitrogen-based fertilizers on a large scale. This allowed food production to increase dramatically and support growing populations across the planet. It is estimated that today, nearly half the global population is fed thanks to this technology. But this advancement also came with consequences. Excess nitrogen in the soil and water has caused ecological imbalances, such as eutrophication of lakes and rivers, and has increased emissions of nitrogen oxides, gases that contribute to the greenhouse effect and the depletion of the ozone layer. Beyond agriculture, nitrogen plays essential roles in industry, medicine, and materials science. Liquid nitrogen, for instance, is used for rapid freezing, the preservation of cells and tissues, and cryogenic experiments. It reaches temperatures below -196 degrees Celsius, allowing the manipulation of substances extremely sensitive to heat. In industrial settings, nitrogen is used as an inert gas to prevent explosions or unwanted chemical reactions. In electronics manufacturing, it protects components during soldering. In space applications, it helps maintain pressurized and safe systems. Even without being reactive, nitrogen exerts its influence discreetly and indispensably, like a chemical guardian of stability. The nitrogen cycle is also a fascinating example of ecological interdependence. Plants absorb nitrogen from the soil. Animals consume it by eating plants, and when they die, they return nitrogen compounds to the environment. Microorganisms convert these substances back into molecular nitrogen, completing the cycle. It is a delicate process that requires balance among all forms of life. Any disruption or excess can cause invisible yet profound disasters, and that is why nitrogen, though silent and unseen, is heard and felt by all living things. It is the thread connecting the atmosphere to biology, respiration to nourishment, the chemistry of the sky to that of our bodies. We breathe its silence, we eat its presence, and we depend on its stability, even without knowing it. On planet Earth, few elements have a relationship with life as intimate as oxygen. Comprising about 21% of the current atmosphere, it is the invisible spark that fuels every breath, every heartbeat, every conscious thought. But it wasn't always this way. For billions of years, Earth was dominated by an oxygen-poor atmosphere, inhabited only by anaerobic organisms, life forms that thrived without this gas. In its early history, oxygen was a toxic byproduct. Only with the emergence of photosynthetic cyanobacteria, around 2.5 billion years ago, did this element begin to be released in large quantities into the atmosphere, triggering an unprecedented event, the Great Oxidation. This process transformed the planet, not just the air we breathe, but its deep chemistry, enabling the rise of complex aerobic life. The oxygen revolution was slow but relentless. As cyanobacteria flooded the oceans and sky with oxygen, Earth underwent profound environmental changes. Iron-rich minerals began to oxidize, forming the vast banded iron formations that we now mine. At the same time, the new oxygenated atmosphere paved the way for organisms that could use this gas as an energy source, and the leap was immense. While anaerobic fermentation produced only 2 molecules of ATP per glucose molecule, aerobic respiration could generate up to 36. This meant a dramatic increase in metabolic efficiency, a breakthrough that allowed for the emergence of more complex, larger, and more specialized cells. Oxygen, therefore, did not merely sustain life, it accelerated its evolution. In today's natural world, oxygen remains vital at every level. It is the essential fuel of the mitochondria, the organelles that function as power plants in animal and plant cells. Every human breath brings trillions of oxygen molecules through the lungs, across the alveoli, into the bloodstream, where they bind to hemoglobin in red blood cells. From there, they are transported to every tissue, every cell, where they participate in cellular respiration. This process transforms glucose into energy, releasing carbon dioxide as a byproduct. It is a constant, rhythmic, silent cycle, and absolutely essential. Oxygen not only keeps us alive, it sets the pace of our metabolism, the heat of our bodies, and even the clarity of our thoughts. Beyond biology, oxygen plays a critical role in chemistry, technology, and medicine. It is the agent behind combustion. All fire depends on oxygen to exist. In the metallurgical industry, oxygen is used to cut and fuse metals. In hospitals, it is delivered in high concentrations to patients with respiratory difficulties, and it is employed in hyperbaric therapies that treat everything from infections to diving accidents. In space environments, it is essential for sustaining life aboard orbital stations and spacecraft. Even in the form of ozone, a molecule made of 3 oxygen atoms, it forms the layer that protects us from the sun's ultraviolet radiation. In all these roles, oxygen reveals its dual nature, vital and volatile, nourishing and oxidizing, necessary and dangerous in excess. But perhaps the most profound aspect of oxygen lies in its connection with time. It ages things. It oxidizes metals, alters molecules, wears down what is organic. The same element that gives life also marks its passage. Oxidation is the cost of aerobic existence. And yet, this delicate balance between energy generation and deterioration defines our biology and our life cycle. Oxygen, with its silent power, shapes everything, from the fire that warms to the final breath. It is not merely a chemical component, it is the link between atmosphere and consciousness. It is present in a baby's first cry, in the fire lit under the stars, in the photosynthesis of tropical forests, and in the breath of each new dawn. Oxygen is, in essence, the breath of Earth. Among the elements that have shaped human civilization, few are as paradoxical as phosphorus. It is not only a chemically essential component of life, present in DNA, bones, muscles, and every cell in the body, but also a symbol of transformation, energy, and even destruction. The name phosphorus comes from the Greek phosphoros, meaning light-bearer, a reference to its property of glowing in the dark due to the phosphorescence of some of its forms. But its history is even more fascinating. It was the first element to be deliberately discovered in a laboratory. Isolated in 1669, by the German alchemist Hennig Brand, who was searching for the legendary Philosopher's Stone by boiling liters of human urine. As the liquid evaporated, he found a residue that glowed in the dark and ignited spontaneously upon contact with air. It was white phosphorus, one of the most dangerous and reactive forms of this enigmatic element. In nature, phosphorus is not found in its pure state, precisely because of its high reactivity. It occurs in minerals like apatite, forming phosphates that are fundamental to Earth's biogeochemical cycles. Within cells, phosphorus is a key part of ATP, adenosine triphosphate, the main energy currency of life. Every muscle contraction, every nerve impulse, every cell division depends on phosphate-related reactions. It is also found in DNA and RNA, forming the backbone of these molecules that store and transmit genetic information. In bones and teeth, phosphorus binds with calcium to form hydroxyapatite, the compound that gives strength and rigidity to our skeleton. Thus, though invisible, phosphorus is the skeleton of life and the spark that moves it. In agriculture, phosphorus plays a role as crucial as nitrogens. Phosphate fertilizers are essential for plant growth, and shortages can threaten global food security. However, unlike nitrogen, which can be synthesized from air, phosphorus comes from limited mineral deposits located in only a few regions of the world. Morocco, China, and the United States hold the majority of these reserves, making phosphorus a strategic geopolitical resource. Excessive use of phosphate fertilizers, on the other hand, has caused serious environmental problems. Phosphorus runoff into rivers and lakes feeds the uncontrolled growth of algae, leading to eutrophication, fish die-offs, and the collapse of entire aquatic ecosystems. Thus, the same element that nourishes crops can, if mismanaged, suffocate life elsewhere. In the industrial and military domains, phosphorus has revealed its darker side. White phosphorus, highly flammable and toxic, has been used in incendiary weapons since the 20th century. Upon contact with air, it burns at over 800 degrees Celsius, sticking to skin and causing deep, continuous burns. For this reason, its use in weaponry has been the subject of ethical and environmental criticism. Even so, this same reactivity is harnessed in controlled ways in everyday products. Phosphates are found in detergents, toothpaste, anti-corrosion treatments, and even certain fireworks. Red phosphorus, a more stable form, is used in the heads of safety matches, the kind we light with a simple strike against a rough surface. Thus, phosphorus continues to oscillate between the useful and the dangerous, between nutrition and combustion. The story of phosphorus is the story of a substance that simultaneously holds the secrets of cellular energy and the dangers of war. An element that stores genetic information and ignites munitions, that feeds the roots of a crop and the flames of a trench. It perhaps personifies, more than any other, the duality of science, the ability to create and to destroy, to illuminate and to burn. Learning to use it wisely is one of the great challenges of modern civilization. And in the end, that may be its greatest lesson. Phosphorus is the light that carries within it the risk of fire, a reminder that all knowledge demands responsibility. On the far left of the periodic table lies a group of elements that seem to defy all rules of chemical stability. These are the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium, known for their extreme reactivity, silvery luster, and almost explosive behavior when in contact with water. These elements belong to Group 1 of the table and share a similar electronic structure. Each has only one electron in its outermost shell. This configuration makes them highly unstable and eager to shed that lone electron, easily forming positive ions. In doing so, they release energy violently. Just a small piece of sodium thrown into water triggers a vigorous reaction, releasing hydrogen gas and enough heat to ignite flames. These metals are so reactive that they must be stored immersed in mineral oil to prevent contact with air moisture, or even oxygen. Despite their explosive nature, alkali metals are essential to life and modern technology. Sodium, for example, is a fundamental component of table salt, sodium chloride, and is vital for the conduction of nerve impulses in the human body. Our neurons and muscle cells depend on the exchange of sodium and potassium ions across cellular membranes to generate electrical signals. Potassium, in turn, is crucial for fluid balance and muscle function. It helps maintain stable blood pressure and is involved in numerous enzymatic processes. These elements, though dangerous in pure form, become essential to life when part of stable compounds. Life, with its remarkable capacity for regulation, uses instability to its advantage. In industry, lithium has become a leading player in the recent technological revolution. It is the core element in rechargeable batteries that power smartphones, laptops, electric vehicles, and even solar energy systems. Lithium-ion batteries are lightweight, long-lasting, and have high energy density, ideal characteristics for the digital, portable world we live in. Lithium is also used in psychiatric treatments, particularly in managing bipolar disorder, once again showing how a reactive element can be transformed into stability when applied correctly. Rubidium and cesium, though less common, are used in scientific research and high-precision atomic clocks, where the regularity of their atomic oscillations allows time to be measured with near-perfect accuracy. Francium, the last of the group, is so rare and unstable that it is virtually unavailable in quantities sufficient for practical use. Its half-life is only 22 minutes, and it exists solely as a product of radioactive decay. Still, its theoretical presence in the table completes the pattern and reinforces the concept of periodicity. All alkali metals share similar trends. The higher the atomic number, the more reactive the metal. This occurs because the solitary outer electron is increasingly distant from the nucleus and less tightly held, making it easier to lose and speeding up reactions. This systematic progression is a clear example of how the periodic table predicts behavior based on position and electron structure. The beauty of alkali metals lies in this dichotomy. They are intensely dangerous and profoundly useful. They are like exposed wires of nature, always ready to react, to release energy, to transform. In their metallic forms, they are like gunpowder wrapped in liquid silver, but in compounds they become nutrients, medicines, technologies. They remind us that even chaos has its place in order, that life and progress often depend on the ability to harness violent forces. Alkali metals, with their raw and primal energy, are messengers of chemical transformation, elements that do not rest, and in their reactions illuminate the path to understanding. Located in the second column of the periodic table, the alkaline earth metals form a family that is less explosive but equally fascinating. Beryllium, magnesium, calcium, strontium, barium, and radium. Each of these elements shares a similar structure, 2 electrons in the outermost shell, making them less reactive than alkali metals but still highly reactive compared to most other metals. Unlike their neighbors in the first column, the alkaline earths do not react violently with water at room temperature, but when heated or under specific conditions, they release hydrogen and heat in a noticeable way. They are silvery, lightweight, conductive metals and remarkably versatile, and throughout history, they have played crucial roles in engineering, medicine, and even in the bones of our bodies. Yes, some of them quite literally support us from within. Calcium is undoubtedly the most familiar of the group, known for its presence in bones and teeth. It is essential for the structural rigidity of the skeleton, but its role goes far beyond physical support. Calcium is vital for muscle contraction, blood clotting, nerve transmission, and even enzyme activation. It acts as an intracellular signaler, triggering biochemical responses that keep the body operating in synchrony. Calcium deficiency can lead to osteoporosis, seizures, and muscle failure, while an excess can also cause serious problems. Geologically, calcium is found as calcium carbonate, the main component of limestone, shells, corals, and marble. These sedimentary rocks, formed over millions of years, are quite literally the fossilized record of ancient marine life. Magnesium, in turn, performs equally important biochemical functions. It is involved in over 300 enzymatic reactions, contributes to DNA and RNA synthesis, regulates muscle and nerve function, and helps control blood sugar levels. In the plant kingdom, magnesium is at the heart of chlorophyll, the molecule that allows plants to perform photosynthesis. Without magnesium, there would be no green leaves, no atmospheric oxygen, and no foundational food chain for the planet. In industrial applications, magnesium is used in lightweight metal alloys, particularly in aerospace, due to its combination of lightness and strength. It is also used in pyrotechnics, as its white flames are intensely bright, lighting up the sky in spectacular displays. Strontium and barium, though less known to the general public, have intriguing properties. Strontium is used in fireworks to produce vivid red flames, in special metal alloys, and in medical research with radioactive isotopes. Barium is essential in radiological exams of the gastrointestinal tract, as its compounds form suspensions opaque to X-rays, allowing internal organs to be visualized in detail. However, soluble barium is toxic, and its use must be carefully controlled. Radium at the end of the group is radioactive, and was historically used in luminous watch dials before the dangers of ionizing radiation were fully understood. Its discovery by Marie Curie was a milestone in radioactivity, but also a warning. Not everything that glows brings light. Beryllium, the lightest of the alkaline earth metals, has properties that make it valuable and dangerous. It is extremely rigid, lightweight, and has a high melting point. It is used in aerospace components, X-ray equipment windows, and telescope mirrors. However, inhalation of beryllium dust can cause severe lung disease, which is why its handling requires strict safety protocols. Thus, the alkaline earth metals remind us of a constant truth in nature. Elements that are highly useful can also be dangerous, depending on form and dose. They are in our structures, our medications, our fireworks, and our physiological systems. They are the building materials of the world and of ourselves. In the grand stage of chemistry, the alkaline earth metals form a bridge between the vigorous reactivity of alkali metals and the stability of transition metals. Their position on the table is not just geographic. It reflects a unique chemical identity, a combination of strength, function, and balance. In every concrete structure, in every heartbeat, in every leaf of lettuce, and every beam of colored light, there is a silent trace of these elements. They remind us that stability is not always immobility. Sometimes, it is precisely what allows everything to function in harmony. If there is one family on the periodic table that embodies the constant tension between utility and danger, it is the halogens. Located in Group 17, right next to the noble gases, these elements are intensely reactive and play a central role in countless chemical processes of everyday life. Fluorine, chlorine, bromine, iodine, and astatine, with tennessine, a synthetic element completing the family, form a lineage of atoms rarely found free in nature. They tend to combine quickly with other elements to form salts and highly stable compounds. The name halogen comes from Greek and means salt former, which is exactly what they do with remarkable efficiency. They react violently with alkali and alkaline earth metals to form salts like sodium chloride, table salt, used to season millions of meals every day. But behind this simplicity lie powerful chemical characteristics, with applications ranging from water disinfection to nuclear medicine. Fluorine is the smallest and most electronegative of the halogens, and this makes it extremely reactive. It corrodes nearly any substance, even glass, and can react explosively with many compounds. Yet when tamed in the form of fluoride, it becomes a dental protector, found in toothpaste and some public water supplies. Fluoride helps remineralize tooth enamel and prevent cavities, a microscopic contribution with a massive impact on public health. Chlorine, perhaps the best-known halogen, is widely used in water purification, swimming pools, and sewage treatment. It acts as a killer of microorganisms, eliminating bacteria, viruses, and protozoa with speed. However, chlorine gas was also used as a chemical weapon during World War I, a reminder of the fine line between remedy and poison. Bromine, a liquid at room temperature, a rare trait among elements, has a discreet but important presence. Used in flame retardants, pharmaceuticals, and analog photography, bromine serves as an intermediate in various organic reactions. It requires careful handling, as it is corrosive and toxic, yet its controlled derivatives are valuable in specific applications. Iodine, on the other hand, is a long-time ally of medicine. Its tincture has been used for centuries as an antiseptic. It is essential for the proper functioning of the thyroid gland, which relies on iodine to synthesize hormones vital to metabolism. Iodine deficiency causes goiter and neurological development issues, which is why many countries implemented iodized salt as a public health policy. Thus, even in tiny amounts, iodine has the power to shape the internal balance of the human body. Astatine, extremely rare and radioactive, is perhaps the least understood naturally occurring element in the entire periodic table. It appears in such minuscule quantities in Earth's crust that most of its study remains theoretical. Even so, Recent research suggests that some of its isotopes may have promising applications in nuclear medicine, particularly in targeted cancer therapies. Tennessine element 117 is a synthetic halogen created in the lab, with a half-life so short that its existence is confirmed only in fractions of a second. Yet its behavior helps scientists better understand the limits of the periodic table and how super-heavy elements can be classified and potentially used. Chemically, halogens share an electronic obsession. They are just one electron away from completing their valence shell. This thirst for stability makes them highly reactive, especially with metals, but also with organic compounds, resulting in a vast array of useful and sometimes dangerous reactions. They appear in disinfectants, pesticides, medications, plastics like PVC, lighting systems, and even anesthetics. They are present in our daily lives in invisible but essential ways. They are chemical soldiers, disciplined, effective, lethal when out of control, but profoundly beneficial when properly employed. In the larger cycle of nature, halogens participate in atmospheric, oceanographic, and biological processes. Their presence in marine organisms, Earth's crust, and even the exosphere shows that, even in trace amounts, these elements are among the most influential on the periodic table. They protect us, heal us, illuminate our lives, and at the same time demand our utmost respect. In essence, they are the reactive guardians of chemical order. And their story teaches us that true power lies not in abundance, but in the intensity with which one can interact with the world. On the right side of the periodic table lies a group of elements as discrete as they are fundamental. These are the noble gases: helium, neon, argon, krypton, xenon, and radon. Each of them occupies a special position in Group 18, characterized by an almost perfect electronic stability. Their outermost electron shells are full, which makes them chemically inert. They barely react with other elements or compounds. This stability is so profound that for decades it was believed they could not form molecules under any circumstances. The term noble itself refers to their isolated nature, as if they were aristocratic elements watching the rest of the table from above, unbothered. And yet, it is precisely this resistance to reaction that makes them so valuable, in applications ranging from lighting to preservation of precious materials, from medicine to space exploration. Helium, the lightest of the group, is famous for its use in balloons, airships, and cryogenic environments. It doesn't burn, it doesn't explode, and its low density makes it ideal for applications where safety and control are vital. In its liquid form, helium reaches temperatures near absolute zero, becoming an irreplaceable tool in magnetic resonance imaging and experiments involving superconductivity. Neon, on the other hand, is associated with the bright red-orange glow of urban neon signs. When subjected to electrical discharge, neon emits intense light, making it a symbol of modernity in the 20th century. Argon, the third in the series, is the most abundant noble gas in Earth's atmosphere, around 1%. It is used as a shielding gas in welding, in semiconductor production, and even in incandescent light bulbs, where it prevents the oxidation of filaments. Further down the table, krypton and xenon exhibit even more intriguing properties. Both are used in specialized lighting systems, such as high-intensity flashes and projection lamps. Xenon, in particular, is used in arc lamps for cinema projectors, car headlights, and even certain types of general anesthesia. It is also employed as a propellant in ion thrusters, which have been successfully tested in space probes. Its high atomic weight and stable behavior make it ideal for generating smooth, continuous thrust in the vacuum of space. Krypton, whose name comes from the Greek kryptos, meaning hidden, is used in lasers and advanced physics research. Both demonstrate that even the quietest elements can have high-impact applications when used precisely. Radon, finally, is the heaviest and the only radioactive noble gas. It forms naturally from the decay of uranium in the ground and can seep into homes through cracks in the soil. Its radioactivity is invisible, but dangerous. Prolonged inhalation of radon is one of the leading causes of lung cancer in regions with high natural concentrations. Even so, its radioactive properties were once explored in experimental medical treatments. Radon serves as a reminder that atomic nobility does not exempt an element from risk. Even chemical stability can mask nuclear instability. From a physical perspective, noble gases have unique characteristics. They are all monoatomic, possess extremely low boiling points, and have specific thermal conductivity. These properties make them ideal as thermal insulators, cooling agents, and protective atmospheres in sensitive environments. They are used in radiation detection chambers, semiconductor manufacturing, particle physics experiments, and biomedical applications. And despite their isolated nature, noble gases serve as connectors between electricity and light, between chemical stability and technological functionality, between the silence of the atom and the activity of the modern world. In the wider universe, noble gases also appear in stars and gas giants. They are detected in planetary atmospheres, in nebulae, and even in meteorites, proving that their discrete presence extends far beyond Earth. They are cosmic travelers, resistant to time and reaction, floating as silent witnesses of matter, and thus their stability becomes a symbol of longevity, precision, and safety. Noble gases do not shine through explosion, they shine through constancy. They are, in their chemical silence, the guardians of atomic order. When we talk about the elements that shaped human civilization, few are as symbolic and essential as iron. Located at the center of the periodic table, part of the transition metals group, iron represents a point of balance between strength, abundance, controlled reactivity, and utility. It is the fourth most abundant element in the Earth's crust, found not only in rocks and minerals such as hematite and magnetite, but also in the planet's core itself, where it is believed that, under extreme pressures and temperatures, iron and nickel form the metallic structure that generates Earth's magnetic field. This field, in turn, protects life from solar radiation and enables a blue sky, calm oceans, and a stable atmosphere. Thus, even invisible to our eyes, iron surrounds us, from the planet's depths to the blood that flows through our veins. The mastery of iron marked a profound shift in human history. When we learned to extract and manipulate this metal through smelting, the Iron Age began, around 1200 before Christ. Unlike copper or bronze, iron required much higher temperatures to be melted and worked, which led to the creation of sophisticated furnaces and the evolution of metallurgical techniques. With it, weapons became stronger, tools more durable, and structures more robust. Cities were built more efficiently, agriculture expanded with more effective plow tools, and empires grew through the military superiority provided by iron swords and spears. In this sense, iron was not just a metal, it was a divider of ages, a catalyst of power and technical progress. In the human body, iron is equally vital. It is present in hemoglobin, the protein responsible for transporting oxygen in the blood. Each hemoglobin molecule contains iron atoms that bind to oxygen in the lungs and release it into the body's tissues. It is because of iron that blood has its characteristic red color. Without it, we could not breathe, think, move, or live. Iron deficiency, known as iron deficiency anemia, causes extreme fatigue, weakness, lack of concentration, and in severe cases can compromise the function of vital organs. On the other hand, excess iron is also harmful, accumulating in organs such as the liver and heart, leading to conditions like hemochromatosis. Once again, chemistry's lesson is clear. Balance is everything. In modern industry, iron is primarily transformed into steel, an alloy produced by adding small amounts of carbon and other elements such as chromium, nickel, or vanadium. Steel is the backbone of global infrastructure, used in bridges, skyscrapers, ships, railroads, tools, machines, and vehicles. There are dozens of types of steel, each with specific properties tailored for strength, flexibility, hardness, or corrosion resistance. Global steel production is so central to the economy that it is used as an indicator of industrial growth. Iron is also found in electric motors, transformers, electromagnets, and a wide range of electronic and electromechanical devices that are part of our daily lives, from refrigerators to subways. Scientifically, iron is also a cosmic protagonist. It represents the energetic limit of stellar fusion. While lighter elements such as hydrogen and helium fuse easily in stellar cores, iron marks the point where fusion becomes energetically unfavorable. When a massive star accumulates iron in its core, it collapses and may explode as a supernova, spreading heavier elements throughout space and restarting the cosmic creation cycle. In this way, iron is both the end of a star and the beginning of new worlds. Each atom of iron in our blood, therefore, carries the memory of a star that died billions of years ago, a silent witness to the cosmic cycle of matter. Iron is not just a material, but a symbolic and functional presence at every level of existence, from engineering to biology, from human history to astrophysics. It mirrors the human condition, strong, necessary, but always seeking balance. With it, we built civilizations, crossed oceans, irrigated fields, raised cathedrals, and won battles. It lives in our tools, our structures, our blood, and our memory. It is the element that gave us structure, literally and metaphorically, to leave the cave and build the modern world. At the heart of the electricity flowing through the walls of our homes, the computers we use, the cell phones in our pockets, and the engines that move the world are two elements whose conductivity and versatility have shaped the modern era: copper and zinc. Both belong to the family of transition metals and have histories deeply intertwined with the advancement of technology, medicine, and social organization itself. Copper, in particular, is one of the first metals ever used by humanity. Its discovery and manipulation predate even the Bronze Age, and its unique properties, malleability and electrical conductivity, have made it a literal and symbolic conductor of human progress. Zinc, often more discreet, is a stabilizer, a silent protector that acts both against corrosion and within the immune system, and it is the essential ingredient that, when combined with copper, gave birth to bronze, the first metallic alloy in history. Copper is an exceptional conductor. Among common metals, it is second only to silver in electrical efficiency, but because it is more abundant and affordable, it became the universal standard for wiring. When you turn on a lamp, power a device, or listen to music through headphones, copper is there, guiding the electrons with minimal resistance. In motors, generators, transformers, and printed circuits, it is the path through which energy flows smoothly. This fluidity also shows in its historical use. Egyptians, Sumerians, Chinese, and Greeks used copper for both utensils and ornaments. In ancient Rome, it was widely used for plumbing and coinage, marking its enduring presence as a symbol of value and functionality. Biologically, copper also plays a vital role. It contributes to the formation of enzymes involved in energy production within cells, collagen formation, skin pigmentation, and the function of the central nervous system. Although needed in small amounts, its presence is indispensable, and both deficiency and excess can cause serious disorders. Zinc, in turn, takes on a more protective and regulatory role. It is crucial for the function of more than 300 enzymes, contributes to DNA replication, wound healing, and strengthening of the immune system. In recent times, its use has expanded with the popularity of dietary supplements and treatments for colds, infections, and metabolic disorders. Zinc deficiency can impair growth, immunity, and neurological development, especially in children and vulnerable populations. In material science, the union of copper and zinc produces bronze, a metallic alloy that revolutionized ancient civilizations. Stronger than pure copper, bronze was used to make tools, weapons, armor, musical instruments, and sculptures. The Bronze Age marked the rise of the first major cities, the beginning of organized warfare, and the flourishing of arts and writing. The alloy was durable, corrosion-resistant, and relatively easy to melt, a huge advantage for societies that had not yet mastered the high temperatures required to smelt iron. In more recent times, zinc has become widely used in galvanization, the process of coating iron with a thin protective layer to prevent oxidation. This significantly extends the lifespan of metal structures, automobiles, appliances, and even entire bridges. Both elements also have applications in microelectronics and renewable energy. Copper is used in solar panels, wind turbines, and electric vehicles, where its excellent conductivity helps maximize energy efficiency. Zinc, meanwhile, is being researched as a basis for next-generation batteries, especially zinc-air batteries, which promise higher energy density and lower environmental impact. Its role in metallic alloys like brass, a mixture of copper and zinc, also remains important in the manufacture of musical instruments, decorative items, and plumbing systems. Thus, they are found in the details of life, from the smooth touch of piano keys to the silent resistance of urban metal structures. Copper and zinc reveal that electricity and engineering are not just fruits of physics, but also of the chemistry of materials. These are elements that conduct more than electric current. They conduct civilizations, health and stability. One offers flow and connection, the other protection and control. Together, they show that the construction of the modern world depends as much on brute strength as on atomic finesse. They are metals with a nervous system's soul, because through them, the modern world feels, responds, and moves. Among all the elements in the periodic table, perhaps none evokes such intense emotions as gold. Positioned among the transition metals with the symbol Au and atomic number 79, gold does not oxidize, degrade over time, or lose its luster. And precisely because of this, it has become a universal symbol of wealth, power, purity, and eternity. Its warm yellow hue is unmistakable and uncommon among metals, and its resistance to corrosion is almost mythological. Throughout history, it has been used as currency, ornament, amulet, object of worship, and imperial standard. Empires have fallen, and civilizations have been decimated in pursuit of its nuggets. And even in the digital age, with markets dominated by cryptocurrencies and electronic circuits, gold remains humanity's oldest safe haven. It is no exaggeration to say that this metal has shaped borders, written histories, and fueled obsessions. Chemically, gold is surprisingly stable. It does not react with oxygen or most acids, enduring through time with a solemn metallic dignity. Only aqua regia, a mixture of hydrochloric and nitric acid, can dissolve it. This chemical stability explains its durability in jewelry, coins, and archaeological artifacts. Many pure gold objects found in millennia-old excavations remain almost unchanged, as if they were forged yesterday. This resistance to aging has given gold a symbolic character, that of an eternal, immortal material. That's why it is used to crown kings, seal wedding alliances, and reward athletic achievements. Gold is not just a metal, it is permanence, status, and glory encapsulated in atoms. Despite all its symbolism, gold also has extremely practical applications. Its electrical conductivity is among the highest of all metals, even surpassing that of copper, and its resistance to oxidation makes it ideal for electrical contacts and high-precision electronic components. It is used in integrated circuits, connectors, space sensors, and medical equipment. Satellites and spacecraft are coated with ultra-thin layers of gold to reflect solar radiation and protect sensitive instruments. In dentistry, gold is still used in restorations and prosthetics due to its biocompatibility and malleability. In nuclear medicine, gold nanoparticles are being explored to deliver drugs directly to tumor cells, offering hope in the treatment of certain cancers. Thus, gold moves elegantly between the showcase and the laboratory. Economically, gold underpins one of humanity's most enduring concepts, value. For centuries, gold coins circulated as the main form of currency. Until the 20th century, most global economies were backed by physical gold reserves, the well-known gold standard. Even in today's dematerialized markets, central banks continue to hold gold as a safeguard in times of instability. Gold is the ultimate asset of trust. It does not depend on governments, cannot be printed, and cannot be destroyed by economic disasters. Its mere existence, in underground vaults and remote mines, anchors the value of currencies, stocks, and even cryptocurrencies backed by tangible commodities. On a psychological level, the fascination with gold seems almost innate, from early hominids who collected shiny stones to modern societies still mesmerized by its aesthetic. Gold traverses history as a collective archetype. It shines in myths, religious relics, crowns, and conquests. It represents the unattainable, the absolute, that which stands above the forces of time and nature. And perhaps that is why gold inspires such greed. Not for its chemical properties or market value, but for the idea that it represents something no other element can offer, the promise of immortality. Silver, with the symbol Ag and atomic number 47, is one of the most versatile, beautiful, and historically symbolic elements in the periodic table. Its reflective surface, with an unmistakable metallic luster, is the brightest among all metals. For millennia, humanity has been captivated not only by its beauty, but also by its practical and symbolic utility. Used in coins, sacred ornaments, utensils, mirrors, cutlery, musical instruments, photography, and even medical treatments, silver has shone both in palaces and hospitals. Unlike gold, which barely reacts, silver is chemically more active, giving it powerful antimicrobial and electronic properties. It is a metal of action. It heals, conducts, purifies, and adorns, and its story is intertwined with the rise of global trade, the advancement of medicine, and the sacred imagination. Silver was one of the first metals to be used in coinage on a large scale. Civilizations such as the Greeks, Romans, Persians, and Chinese minted silver coins to standardize transactions and facilitate trade. For a long time, silver was valued as much as gold, and in some contexts even more. In the Middle Ages, the silver routes from the Americas to Europe funded empires, wars, and revolutions. The mines of Potosi in present-day Bolivia produced so much silver that people said a bridge of metal could be built all the way to Spain from what was extracted. Silver was not just money, it was political and military power. It became the invisible fuel of colonial empires, global markets, and commercial networks that connected continents through oceans and wars. In medicine, silver has gained prominence for its antibacterial action. Long before the discovery of antibiotics, silver-based solutions were used to treat wounds, burns, and infections. Silver vessels were used to preserve drinking water and milk by inhibiting microbial growth. Even today, materials impregnated with silver ions are used in bandages, catheters, hospital garments, and medical devices to reduce infections. Silver nitrate, for example, was used for decades in newborns' eyes to prevent blindness caused by infections during childbirth. Colloidal silver, suspensions of metallic silver particles, is still being studied for its antimicrobial potential, though uncontrolled use can pose risks such as argyria, a rare condition in which the skin turns permanently bluish-gray. In electronics and modern industry, silver is also irreplaceable. Among all metals, it has the highest electrical and thermal conductivity, making it essential for manufacturing electrical contacts, soldering materials, solar panels, photovoltaic cells, sensors, and printed circuit boards. It operates behind the scenes in nearly all modern electronic devices, albeit in minute quantities. This makes it invisible to the common eye, but absolutely essential. The rise of renewable energy, especially solar power, increasingly relies on silver-based technologies. And even in emerging technologies such as nanotechnology and smart materials, its chemical properties continue to be explored with fascination and precision. From a symbolic and cultural perspective, silver carries a complex meaning. In esoteric and religious traditions, it is associated with the moon, intuition, protection, and purification. While gold is the metal of the sun, glory, and royalty, silver is the metal of the sacred feminine, mystery, and healing. It is used in blessing rituals, protective amulets, and liturgical tools. In stories and legends, silver bullets kill werewolves, silver mirrors reveal hidden truths, and silver chains ward off invisible forces. This collective imagination shows how silver goes beyond commercial value to occupy a profound symbolic space, as something that protects, reflects, and connects worlds. Silver, in its reflective nature, may be the perfect mirror of the human condition, beautiful and sensitive, practical and symbolic, useful and mysterious. It shines in details, in discrete surfaces, in the hidden circuits that keep modernity functioning. It's in the coin, the scalpel, the ring, and the chip. And like moonlight, its presence is gentle yet constant, illuminating what must be seen, healing what must be touched, and reflecting with metallic elegance the invisible paths that science and history have traced through the centuries. Mercury is one of the most intriguing and enigmatic elements on the periodic table. With the symbol Hg and atomic number 80, it is the only metal that remains liquid at room temperature, making it a visible and fascinating exception to the usual rules of matter. Fluid, silvery, mirror-like, and dense, Mercury defies categorization. It challenges the senses, flowing like a liquid, weighing like a metal, shining like a mirror, and moving with an almost hypnotic smoothness. Its name comes from the Roman god Mercury, messenger of the gods and symbol of speed and transformation. The name is no coincidence. Mercury is an element of change, of infiltration, of slipping through both fingers and certainties. It can be beautiful and deadly, precise and dangerous, useful and toxic, all at once. Historically, mercury played a central role in alchemy. Known as quicksilver, it was believed to be one of the fundamental components of all metals, a kind of primordial metallic essence. Alchemists sought to transmute base metals into gold, believing mercury to be the key to this transformation. Even after the fall of alchemy and the rise of modern chemistry, mercury remained important. Thermometers, barometers, manometers, and other measuring instruments relied on its thermal sensitivity and density. It expanded and contracted with temperature changes in predictable ways, making it a symbol of precision for centuries. The silvery column rising in a thermometer is, in itself, a spectacle of physics in motion. But the fascination with mercury hides a darker side. It is highly toxic, especially in the form of vapors or organic compounds, such as methylmercury. Prolonged exposure can cause severe neurological damage, motor coordination loss, cognitive impairment, and in extreme cases, death. Historical cases, like the Minamata tragedy in Japan, where mercury waste dumped into industrial waters led to mass contamination of entire communities, underscore the silent danger of this metal. Even in small amounts, mercury can bioaccumulate through the food chain, affecting fish, birds, and mammals. For this reason, its use has been heavily restricted in many industries, and the search for safer alternatives in tools and processes has become a global priority. Even so, mercury still plays a role in specialized applications. It is used in fluorescent lamps, where small amounts of mercury vapor are electrically excited to produce ultraviolet light, which is then converted into visible light by phosphors. It is also used in certain industrial processes, in high-precision scientific instruments, and remains in use in some dental amalgams, though these are increasingly falling out of favor. Mercury also has radioactive isotopes used in nuclear research and as chemical tracers. Handling mercury, however, requires strict safety protocols, controlled environments, and a deep understanding of the risks involved. Culturally, mercury is rich in symbolism. Because it is liquid and mutable, it is often associated with instability, transformation, and duality. In many esoteric traditions, it represents the bridge between body and spirit, between the material and the unseen. Its image appears in Hermetic texts, Renaissance treatises, and even in astrology, where it symbolizes communication and intellect. In ancient medicine, it was used to treat syphilis and other diseases, though the side effects were often worse than the illness itself. Mercury has always been a dangerous remedy, a solution that demanded faith and courage. In the end, mercury is a reminder of nature's complexity. It does not easily fit into patterns, nor does it behave as expected, forcing us to reconsider the boundaries between solid and liquid, between useful and harmful, between beauty and poison. Its silvery glow continues to fascinate scientists and artists alike, but it demands respect and caution. Mercury is the metal that slips away, that whispers rather than shouts, that flows where others break, a moving mirror of what is at once visible and mysterious. Aluminum, with the symbol Al and atomic number 13, is one of the most common elements in our daily lives, yet also one of the most discreet in its presence. Lightweight, durable, abundant, and incredibly versatile, it evolved from a laboratory rarity to an industrial protagonist in less than 2 centuries. Today it's found in airplanes, cars, cell phones, packaging, household utensils, architectural structures, electrical wiring, and even in medications. It's the third most abundant element in Earth's crust, behind only oxygen and silicon, but its isolation as a pure metal only became possible in the 19th century. Before that, aluminum existed only as part of minerals, such as bauxite, from which it is still extracted today. What makes it remarkable is not just its lightness or abundance, but the fact that it has become a symbol of a silent revolution that reshaped the modern world without fanfare, replacing heavier and more expensive metals with efficient, sustainable, and economical solutions. The history of aluminum is a curious one. In the early 19th century, it was considered more precious than gold. In fact, at the 1855 Paris World's Fair, Napoleon III displayed aluminum cutlery for special guests, while others used silver utensils. The reason was simple. Extracting metallic aluminum from bauxite required complex and energy-intensive chemical processes, which limited its production. That changed radically with the invention of the Hall-Héroult process in 1886, an electrochemical technique that uses electric current to separate aluminum from molten aluminum oxide. This discovery revolutionized metallurgy and enabled mass production, drastically reducing costs. What was once a metal of the elite became accessible to industries, engineers, and the general public. And so began the age of aluminum. One of aluminum's most defining traits is its lightness. It weighs about 1/3 as much as steel, and yet offers high structural strength when combined into alloys. This makes it ideal for applications where weight is critical. In aviation, for example, its introduction allowed aircraft to fly farther, consume less fuel, and carry heavier payloads. In the automotive sector, aluminum is replacing heavy components, contributing to more fuel-efficient vehicles with lower carbon emissions. In the aerospace industry, it is essential for building rockets, satellites, and structural components of space missions. Its weight-to-strength to durability ratio is simply unmatched. Even in less obvious areas like packaging, it shines. Soda cans, aluminum foil, and food containers take advantage of its malleability, impermeability, and ability to protect against light, moisture, and microorganisms. Beyond its industrial applications, aluminum also stands out for its corrosion resistance. When exposed to air, it instantly forms a thin layer of aluminum oxide on its surface, which protects it from further chemical reactions. This behavior makes it ideal for outdoor and marine environments, where many metals would degrade quickly. In construction, it's used in windows, doors, facades, and architectural structures that require durability with lightness. Its ability to reflect light and heat is also utilized in thermal coatings and solar panels. In electrical systems, although not as conductive as copper, its lightweight makes it advantageous for long-distance transmission lines, where weight reduction lowers structural risks and costs. In medicine and healthcare, aluminum appears in antacids, vaccines as an adjuvant, and surgical tools. Despite its widespread use, it has also been the subject of studies regarding toxicity at high levels, particularly concerning potential neurological effects. However, when properly dosed and handled, it remains safe and useful across various clinical applications. Aluminum recycling, in turn, is among the most efficient in modern industry. Unlike some other metals, it can be recycled indefinitely without quality loss, and the process consumes only 5% of the energy required for its original production. This makes aluminum a powerful ally in the fight for sustainability, circular economy, and environmental preservation. Aluminum is therefore the element of pragmatic modernity. It doesn't shine like gold, doesn't fascinate like mercury, nor does it challenge like uranium, but it builds. It connects bridges, protects food, transports dreams, and supports structures. Its presence is so constant that it has become invisible, even though it's in almost everything we touch. It represents the union of science, engineering, and efficiency. The aluminum revolution wasn't loud, but it was solid. It transformed the world not by being rare, but by being reliable. And like any true pillar, its strength lies precisely in its discretion. In the vast territory of the periodic table, there is a group of elements that not only chemically bridge the metallic and non-metallic extremes, but also literally and symbolically support the foundation of nearly all modern infrastructure, the transition elements. Located in the central block of the table, between groups 3 and 12, these metals possess complex electronic structures with partially filled inner shells. It is this configuration that gives them a unique combination of properties: hardness, resistance, malleability, high melting points, multiple oxidation states, and above all, the ability to form stable alloys and complexes. Iron, copper, zinc, nickel, titanium, chromium, manganese, molybdenum, tungsten, platinum, gold, and silver are just a few of the key members of this vast family. Without them, there would be no engines, buildings, tools, electronics, catalysts, paints, medicines, coins, or bridges. Transition elements are, in essence, the muscles and nerves of modern engineering. One of the most important features of these metals is their chemical versatility. Unlike alkali and alkaline earth metals, which typically form only one type of ion, Transition elements can exhibit multiple oxidation states. This means the same atom can lose different numbers of electrons, forming compounds with diverse properties. Iron, for example, can exist as Fe2+ or Fe3+, each behaving differently in chemical solutions. Manganese has oxidation states ranging from +2 to +7, making it useful in a wide range of applications, from batteries to catalysts. This flexibility makes them ideal for industrial processes that require fine control of reactivity, thermal stability, and corrosion resistance. As a result, they are widely used in specialized metal alloys, complex chemical reactions, and high-performance devices. Titanium is one of the most emblematic of this family in terms of strength and lightness. Its alloys are used in aircraft, surgical implants, prosthetics, rocket structures, and elite sports equipment. It has high corrosion resistance, even in extremely harsh environments such as salt water or bodily fluids. Tungsten, with the highest melting point of all metals, above 3,400 degrees Celsius, is essential for making lamp filaments, welding electrodes, and high-temperature resistant alloys. Molybdenum, meanwhile, is vital in stainless steel alloys, enhancing hardness and corrosion resistance. Even in small amounts, these elements completely transform the properties of a base material, enabling the construction of components that operate under extreme stress, temperature, or pressure. In chemical and environmental processes, transition elements also play a crucial role. Platinum, palladium, and rhodium are used as catalysts in industrial reactions and automotive catalytic converters, helping to turn toxic gases into less harmful substances. Vanadium is used in the production of flow batteries, a promising technology for large-scale renewable energy storage. Chromium, despite its toxicity in certain forms, is used to protect metal surfaces from oxidation and wear, as seen in popular chrome plating. Many of these metals display vibrant colors when in solution, making them valuable in pigments, specialty glass, ceramics, and sensors. Their colored ions, like the blue of copper, the green of nickel, or the violet of chromium, have fascinated laboratories and showrooms for centuries. Economically, transition elements form the backbone of the global industry. They are extracted on a large scale, transported through complex logistics chains, and traded in stock exchanges as strategic commodities. A shortage of just one of these elements can have huge repercussions on the production of vehicles, electronics, turbines, medical equipment, and even national currencies. Some, like cobalt and niobium, are considered critical for the energy and military security of many nations, leading to geopolitical disputes over mining regions and control of reserves. Others, like nickel, have gained prominence with the rise of electromobility, being used in electric vehicle batteries and superalloys for aircraft engines and nuclear reactors. Ultimately, transition elements represent the essence of applied chemistry. They are what allow matter to be transformed into solutions, structures, technologies, and innovations. Every steel bridge, pacemaker, computer chip, and jet turbine carries within it the silent work of these adaptable and multifaceted atoms. They are nature's engineering, shaped in minerals, fired in furnaces, and refined into alloys. And even as the world advances toward composite materials, nanomaterials, and new conductors, it is almost certain that transition elements will continue to play a central role, connecting the metallurgical past to the technological future with the same strength as always. Among the elements that have shaped the 21st century with discretion and depth, none stands out quite like lithium. With the symbol Li and atomic number 3, lithium is the lightest of all metals, belonging to the alkali metal family. Its silvery appearance, extremely low density, and high reactivity with water already make it unique, but it is its ability to efficiently store and release energy that has transformed it into the protagonist of a quiet yet global revolution. In just a few years, lithium has gone from a laboratory curiosity to a strategic resource, underpinning the era of smartphones, laptops, electric vehicles, and solar energy storage. Today, wherever there is mobility and energy autonomy, there is lithium, unseen to the eye yet essential to functionality. The chemistry of lithium is remarkable. Its small atomic size and single valence electron allow it to move easily through electrolytes in rechargeable batteries. This behavior makes it ideal for electrochemical cells, where efficient ion transfer is critical. Lithium-ion batteries, developed commercially in the 1990s, offer high energy density, low weight, long lifespan, and the ability to be recharged hundreds of times without significant performance loss. This combination of traits is perfect for portable devices and electric vehicles, enabling a freedom of movement that has redefined personal technology and urban mobility. Unsurprisingly, the three scientists behind the development of lithium batteries were awarded the Nobel Prize in Chemistry in 2019. Lithium's presence extends far beyond electronics. It is used in lightweight metal alloys, specialty ceramics, high-performance lubricants, and even in psychiatric treatments. Lithium compounds such as lithium carbonate have been prescribed for decades to stabilize the moods of patients with bipolar disorder, helping regulate manic and depressive episodes. This medical use reveals an intriguing duality. The same element that powers machines also helps balance the human mind. In industrial systems, lithium also contributes to the manufacture of heat-resistant glass, high-temperature greases, and serves as a fluxing agent in aluminum production. It is a multifaceted element, versatile across scales from the nanometer to the kilometer. From a geopolitical standpoint, lithium has become one of the most strategic resources of the contemporary world. The largest known reserves are concentrated in the so-called lithium triangle, a region encompassing parts of Bolivia, Argentina, and Chile, where dry salt lakes contain vast amounts of the mineral in underground brines. Other key producers include Australia, China, and the United States. The growing demand for rechargeable batteries has turned these regions into targets of billion-dollar investments, political disputes, and environmental debates. Lithium extraction, especially from brines, requires large volumes of water and can impact fragile ecosystems. The lithium rush therefore raises ethical questions about natural resource exploitation, technological sovereignty, and environmental justice. At the same time, scientific research continues to pursue ways to make lithium use more sustainable, efficient, and safe. Solid-state batteries, which replace liquid electrolytes with solid materials, promise greater thermal stability and energy density. Other efforts aim to efficiently recycle used batteries, recovering lithium and other critical metals. Studies are also exploring batteries that use pure metallic lithium, more energy-dense but still unstable. Every breakthrough in this field has the potential to redefine how we store and distribute energy, leading us toward a cleaner, more autonomous, electric future. In this sense, lithium is not just a metal, it is a promise of energy transition. Lithium is, in essence, the lightweight blood of modern machines. It pulses through the invisible arteries of portable technology, allowing the world to move without being tethered to cables or fossil fuels. It embodies the paradox of lightness and power, of atomic simplicity and functional complexity. It seeps silently into daily life, yet carries the weight of a new era. Whether lighting up a phone screen, starting an electric car, or storing solar energy for an entire home, we are, albeit indirectly, touching the precise chemistry of lithium, and with it, one of the greatest technological transformations of our time. Among the most feared, revered, and politically sensitive elements on the periodic table, few carry the historical, energetic, and symbolic weight of uranium and plutonium. With atomic numbers 92 and 94 respectively, these heavy metals belong to the actinide series, a group of radioactive elements whose atomic instability conceals immense power. These elements are capable of performing a rare feat in nature, nuclear fission. When their nuclei are struck by a neutron, they can split into two smaller fragments, releasing an enormous amount of energy, along with more neutrons that sustain the chain reaction. This property has made uranium and plutonium key sources of energy for nuclear reactors, raw material for weapons of mass destruction, and pillars of international politics throughout the 20th century. Here, chemistry found its most intense expression, where atoms ceased to be mere invisible components of matter and became forces capable of determining the course of human history. Uranium occurs naturally in the Earth's crust and is more abundant than silver, for instance. However, only a tiny fraction of natural uranium, specifically the U-235 isotope, is fissile. Most of it consists of U-238, which does not undergo spontaneous fission in practical terms. Therefore, using uranium for energy production requires enrichment, a technically complex and highly sensitive process that isolates enough U-235 for civilian, reactor-grade, or military, weapons-grade purposes. Plutonium, on the other hand, does not exist in significant natural quantities. It is synthetically produced in nuclear reactors when U-238 captures neutrons. Its most utilized isotope, Pu-239, is highly fissile and was the fuel used in the bomb dropped on Nagasaki in 1945. The energy contained in just 1 kilogram of plutonium is equivalent to that of hundreds of tons of conventional explosives, a density of power that is both fascinating and terrifying. In nuclear reactors, both uranium and plutonium are used to produce heat through controlled fission. This heat is used to generate steam, which drives turbines to produce electricity. The process does not emit carbon dioxide directly, making nuclear energy an attractive alternative in the fight against climate change. Countries like France, Japan, Russia, and the United States operate extensive networks of reactors for electricity generation. At the same time, the waste produced by this technology presents significant challenges. It remains radioactive for thousands of years and must be safely stored in deep geological facilities. The risk of accidents, such as those at Chernobyl and Fukushima, continues to fuel debates about the ethical and environmental boundaries of nuclear energy. The same reaction that powers cities can, if it gets out of control, devastate entire regions within minutes. From a military perspective, uranium and plutonium represent the pinnacle of warfare technology. The development of nuclear weapons not only redefined armed conflict, but also ushered in a new geopolitical era, that of deterrence. During the Cold War, the mere existence of massive nuclear arsenals in the United States and the Soviet Union prevented direct confrontations out of fear of mutual destruction. Nuclear proliferation became a global concern, and institutions like the International Atomic Energy Agency, IAEA, were created to monitor the peaceful use of these elements. Even today, access to enriched uranium and plutonium remains one of the most sensitive topics in international diplomacy, involving treaties, inspections, and tensions between nations. Despite all of this, uranium and plutonium also have scientific and medical uses. Certain isotopes derived from these elements are used to date rocks, produce radioisotopes for cancer treatment, and even provide heat for space probes exploring the far reaches of the solar system, such as Voyager and Cassini. In radioisotope thermoelectric generators, small amounts of plutonium-238 generate continuous heat for decades, powering instruments where solar panels are ineffective. Thus, these elements, often associated with destruction, also support science, medicine, and the peaceful exploration of the cosmos. The same unstable nucleus that can obliterate a city can also sustain a lone spacecraft billions of kilometers from Earth. Uranium and plutonium are the most dramatic portraits of the paradox of modern science. They are sources of unlimited energy and of fear. They are medicine and threat, solution and dilemma. They represent the moment humanity learned to manipulate the heart of the atom, and in doing so, gained the power to illuminate the planet or extinguish it. These elements are not just substances. They are choices. They are warnings. They are permanent reminders that knowledge, no matter how advanced, is never separate from ethical, political, and environmental responsibility. Inside every unstable nucleus pulses the deepest lesson of science. Power without conscience is always a risk. Radium, the chemical element with the symbol Ra and atomic number 88, carries one of the most ironic names in the history of science. When it was discovered by Marie and Pierre Curie in 1898, the news literally glowed. Radium emits a greenish phosphorescent light, and its radioactivity seemed almost magical, a new frontier for medicine, industry, and the very understanding of matter. Initially, radium was hailed as a scientific miracle. Its radiation was seen as a symbol of energy, vitality, and progress. It was incorporated into cosmetics, beverages, toothpaste, and even chocolate. But soon, radioactive reality revealed its full cruelty. The same glow that fascinated also slowly killed. And in the early 20th century, with a group of young American factory workers, the world came to understand the price of enchantment with the invisible. This is the story of the Radium Girls, and how radium went from luminous promise to a permanent warning about the limits of science and capitalism. The Radium Girls worked in the factories of the United States Radium Corporation in New Jersey, around the 1910s, the company produced glow-in-the-dark watch dials painted with a compound of radium mixed with zinc sulfide. These workers, many of them teenagers, were tasked with painting the tiny numbers on the dials using extremely fine brushes. To maintain precision, they were instructed to sharpen the brushes with their lips, a practice known as lip pointing. Unknowingly, they ingested traces of radium every day, and the more dials they painted, the more radioactive material accumulated in their bodies, in their teeth, bones, and marrow. The exposure was continuous and internal, and the effects didn't take long to manifest. The first victims began suffering from severe and mysterious symptoms: bone pain, spontaneous fractures, jaw necrosis, tumors, internal bleeding, and a kind of fulminant anemia. Many died young without a clear diagnosis, while the company insisted the products were safe. Some women, while brushing their hair or looking in the mirror, noticed that their teeth glowed in the dark. The horror was silent and relentless. In 1927, 5 of these women, known as the Radium Girls, sued the company. The legal battle was grueling, closely followed by the press and marked by corporate cover-ups. But the case became a turning point. They won. And in doing so, they paved the way for labor protection laws, regulation of radioactive materials, and a deep reassessment of the relationship between science, industry, and ethical responsibility. Chemically, radium is an extremely radioactive alkaline earth metal with a relatively short half-life compared to others in its category. Its primary early use was in radiotherapy, where its intense radiation could destroy cancer cells. For a time it was used as a radiation source in cancer treatments, but it was soon replaced by safer and more controllable alternatives. Today, handling radium requires strict safety protocols. Nevertheless, the story of its discovery and initial use remains a landmark example of the imbalance between scientific enthusiasm and precaution. Radioactivity, once a fascinating novelty, proved to be a force that demands absolute respect and that extracts a high price when underestimated. The case of the Radium Girls left lasting legacies. It was one of the first instances where women sued large corporations for unsafe working conditions. It served as a catalyst for the creation of OSHA, the Occupational Safety and Health Administration in the United States, and inspired environmental justice and labor protection movements. It also profoundly influenced biomedical research into the effects of radiation on the human body. What was once invisible is now monitored, regulated, and feared. The green glow of radium has been replaced by warning labels. The beauty of radioactive light gave way to respect for the invisible atomic forces that can heal, but also kill. Radium, therefore, is not just a chemical element. It is a reminder that the glow of science must not blind critical thinking, that every technological advance comes with ethical responsibility. That knowledge cannot walk separate from care. It taught us that human curiosity must be tempered with caution, and that true progress is only valid when it does not sacrifice the most vulnerable. The light of radium, which once dazzled salons and shop windows, now shines as a warning, subtle, invisible, but eternal. In the middle of the periodic table, discreetly positioned in Group 7, resides an element that does not occur naturally on Earth, and yet has radically transformed the way we see the human body from within: technetium. With the symbol Tc and atomic number 43, technetium was the first element to be artificially produced in a laboratory, and its name, derived from the Greek teknetos, meaning artificial, already reveals its singular nature. Technetium is a silvery metal, radioactive, unstable, and short-lived. These characteristics, which might seem like disadvantages, have in fact made it the invisible star of one of the most important fields in modern medicine: nuclear medicine imaging. In hospitals around the world, millions of diagnostic scans each year rely on the chemistry and physical behavior of technetium, an element that never existed stably in nature, but today is a cornerstone of life-saving science. Technetium-99m, a metastable isomer of the element, is its most widely used isotope. It emits gamma radiation that is highly detectable by imaging equipment, but with enough energy to pass through the human body without causing significant tissue damage. Additionally, it has a short half-life, around 6 hours, meaning it quickly disappears from the body after the exam, reducing risk to the patient. These properties make technetium-99mm the ideal radioisotope for scintigraphy, a type of scan that allows precise visualization of how organs such as the heart, brain, kidneys, and thyroid are functioning, and can even detect bone metastases. This technology not only shows structures, but reveals functions, something conventional X-rays cannot do. To be used in medical imaging, technetium is produced from the decay of molybdenum-99, another radioactive isotope that naturally breaks down into technetium-99 Men. This process takes place in hospital generators known as technetium cows, where the substance is extracted daily, like fresh milk, ready to be incorporated into compounds that bind to specific tissues in the human body. Once injected, technetium concentrates in medically relevant areas, such as lesions, tumors, or regions with altered metabolism, and its radiation is captured by special cameras that generate three-dimensional images of the body's interior. What was once invisible and silent can now be visualized in real time, guiding diagnoses, clinical decisions, and personalized treatments. The impact of technetium's introduction into medicine was revolutionary. Before its use, investigating internal dysfunctions often required exploratory surgery or clinical assumptions based on subjective symptoms. With scintigraphy, it became possible to monitor heart function, assess kidney filtration, identify brain regions with altered blood flow, detect hidden fractures, track cancer treatment progress, and much more, all with safety, speed, and precision. More than 80% of nuclear medicine exams worldwide use technetium-99 Me, and its contribution to early disease detection has saved millions of lives. It is undoubtedly one of the most widely used elements in everyday medical practice, although most patients are unaware of its name or origin. As with any radioactive element, the use of technetium involves strict precautions in handling, disposal, and exposure. Professionals working with it are trained to minimize unnecessary doses, use proper shielding, and follow protocols established by radiation safety agencies. At the same time, global production of molybdenum-99, and therefore of technetium-99 depends on a few nuclear reactors worldwide, making its supply vulnerable to disruptions and requiring ongoing investment in research and infrastructure. For this reason, research centers are developing alternatives such as hospital-based cyclotrons and new decentralized production methods to ensure continued access to this essential resource. Technetium is, in essence, a paradox, an artificial, unstable, and invisible metal that saves lives every day. It doesn't build bridges, conduct electricity, or sparkle in jewelry, but it shines silently on diagnostic monitors, revealing the secrets hidden beneath the skin with precision and discretion. It is a symbol of modern science, capable of turning the fleeting into a tool, the unstable into an ally, the invisible into an image. And as long as it continues to operate behind the scenes of medicine, technetium will remain a constant reminder that often the most fragile elements support the most enduring advances. With the symbol Co and atomic number 27, cobalt is a transition metal that resides in the center of the periodic table and paradoxically also at the center of many high-impact medical and industrial therapies. Historically confused with iron ores, cobalt was isolated as an element in the 18th century, though its name had been used long before, derived from the German word kobold, meaning goblin or evil spirit. In the Middle Ages, miners believed certain ores that released toxic gases and yielded no iron were cursed by mountain kobolds. Little did they know they were handling an element that would one day become one of medicine's primary tools in the fight against cancer, the radioactive isotope cobalt-60. Its intense emission of gamma radiation revolutionized modern radiotherapy and to this day represents hope and healing for millions of people. Natural cobalt is a hard, silvery magnetic metal, widely used in metal alloys for turbines, jet engines, wear-resistant tools, and permanent magnets. It is also present in vitamin B12, an essential nutrient for the production of red blood cells and the proper functioning of the human nervous system. This organic form of cobalt is vital, but in high doses, or when incorporated as unstable isotopes, cobalt can become dangerous. It is precisely this instability, carefully controlled, that allows cobalt-60 to act as a therapeutic radiation source. It emits beta particles and high-penetration gamma rays capable of destroying localized tumor cells without the need for invasive surgery. Radiotherapy machines using cobalt-60, also known as cobalt bombs, operate in a relatively simple yet ingenious manner. The radioactive isotope is encapsulated in a shielded container, and the radiation is released in precisely directed beams. These beams pass through healthy tissues and deposit their energy primarily in cancerous cells, which have a lower capacity to repair DNA damage caused by radiation. For decades, cobalt-60 was the leading radiation source used in oncology. Although it has been partially replaced by more advanced linear accelerators, it is still widely used in regions with limited access to high-end technology. It is a clear example of how science can convert a threat into a solution when handled with responsibility and knowledge. Beyond medicine, cobalt-60 is used to sterilize medical equipment, syringes, gloves, and even food products, eliminating bacteria, fungi, and viruses without leaving residue. It is also employed in industrial radiography to inspect welds and metal structures, revealing internal flaws without disassembly. In archaeology and materials engineering, techniques like neutron activation use cobalt to identify the composition of ancient artifacts or modern alloys with atomic precision. However, due to its radioactive potential, cobalt-60 is also closely monitored by international nuclear safety agencies, as it could be used in malicious radiological devices, such as the so-called dirty bomb. Visually, cobalt has also enchanted humanity. Cobalt compounds such as cobalt-30 illuminate produce an intense blue pigment that has been used for centuries in porcelain, glass, paints, and ceramics. This cobalt blue is deep, vibrant, and enduring, visible in Gothic cathedrals, Portuguese tiles, Renaissance artworks, and even in the visual branding of medicine bottles and cosmetics. In this way, cobalt offers the world both invisible precision and perceptible beauty. It operates in the unseen spectrum of therapeutic radiation, yet also in the visible spectrum of aesthetics, history, and art. Cobalt, therefore, is an element that inhabits multiple worlds: biological, industrial, medical, visual, and even symbolic. It is both nutrient and medicine, both color and energy, both solution and risk. It embodies the duality of matter. The same atom that can paint the sky a deep blue can also kill malignant cells with surgical precision. At its core pulses a force that must be contained, measured, and directed. And when this happens, cobalt ceases to be a kobold of medieval mines and becomes an instrument of healing, a bluish spark in the fight against the invisible. If there is one element that can be identified as the invisible foundation of the modern world, that element is silicon. With the symbol C and atomic number 14, silicon is a metalloid, or semi-metal, strategically positioned on the periodic table at the boundary between metallic conductors and non-metallic insulators. This duality makes it special. It can conduct electricity, but only under controlled conditions, a property essential for the creation of transistors, microchips, and integrated circuits. In other words, silicon is the mineral brain behind the digital revolution. It is present in every computer, cell phone, satellite, solar panel, communication network, and electronic device. When you touch a screen, send a message, access a satellite, or edit a video, you are indirectly interacting with silicon atoms sculpted with atomic precision. Silicon is the second most abundant element in Earth's crust, second only to oxygen. It is found in sand, rocks, clays, and minerals like quartz. However, for electronic use, it must be in its purest form, monocrystalline silicon. The production of this material requires sophisticated purification and crystallization processes, such as the Czochralski method, which grows large, flawless cylinders of pure silicon, later sliced into ultra-thin wafers. These wafers serve as the base where microcircuits are etched using extremely precise lithography, creating the millions, now billions, of transistors that form the core of every processor. These tiny digital switches, turning on and off at astonishing speeds, are the foundation of binary code that executes everything from mathematical calculations to video game graphics. The semiconductor industry, built around silicon, is one of the most complex and sophisticated in the world. The required purity exceeds 99.99999%, and miniaturization has reached the nanometer scale, smaller than a bacterium. Chip factories, known as fabs, are hyper-controlled environments with air filtration systems cleaner than those in surgical rooms. Control over this production chain carries deep geopolitical implications. Countries such as Taiwan, South Korea, the United States and China are not merely competing for silicon dominance. They are vying for supremacy in artificial intelligence, industrial automation, cyber defense, and global critical infrastructure. Silicon, which began as sand, has become a strategic currency of global power. But silicon's role is not limited to computing. It is also at the heart of the energy revolution. Photovoltaic silicon solar panels capture sunlight and convert it into electricity, offering one of the most promising and sustainable solutions to the climate crisis. Its semiconductor properties allow electrons to be released when struck by solar photons, generating clean and continuous electrical current. These panels are becoming more efficient while decreasing in cost, which has fueled their adoption in homes, industries, and even space satellites. Silicon has thus become not just the medium of information, but also the conductor of future energy. In biology, although it is not essential for all organisms, silicon plays important roles in certain species. Diatoms, aquatic microalgae, construct intricate and delicate silica-based structures, true works of microscopic architecture. Plants such as bamboo and rice also incorporate silicon into their tissues, gaining mechanical strength and protection against pests. In medicine, silicon compounds are used in implants, prosthetics, contact lenses, and as components of biocompatible silicones used in surgery and aesthetics. In a way, silicon spans every domain, from desert sand to human eyes, from solar panels to the brains of machines. Culturally, silicon has also left its mark. Silicon Valley has become synonymous with innovation, technology, and social transformation. It is where the major digital corporations, social networks, and operating systems that connect billions of people were born. The region's name is no coincidence. It is a direct homage to the chemical element that made all this revolution possible. It is a living metaphor for the capacity to transform raw material into conceptual upheaval, to shape atoms in order to shape societies. Silicon does not merely power chips, it powers the times, and perhaps this is its greatest lesson, that even the most common elements, like a grain of sand, can conceal infinite potential when understood, refined, and applied with intelligence. Silicon is the mirror of the information age, cold, precise, silent, yet capable of processing billions of decisions per second. It is an example of how the periodic table, far beyond a catalogue of substances, is the blueprint of the modern world, invisible to the eye, yet etched into every pixel of reality. With the symbol C and atomic number 34, selenium is one of the most discrete elements on the periodic table, and yet one of the most intriguing when it comes to human health. It is classified as a non-metal and belongs to the same group as sulfur and oxygen. It has no metallic shine, forms no grand structures, and does not drive explosive reactions. However, in microscopic amounts, it participates in vital functions within the human body. And as with many micronutrients, balance is everything. Both deficiency and excess can be dangerous. Selenium challenges extremes. It is both antioxidant and toxic, both shield and poison, both essential and mysterious. It is living proof that in the chemical world, what often matters is not how much there is, but where and how it manifests. In nature, selenium is relatively rare. It is found in small concentrations in copper, lead, and nickel ores, and its forms vary between inorganic and organic compounds. In the human body, its primary role is related to protection against oxidative stress. Selenium is part of the enzyme glutathione peroxidase, one of the main cellular mechanisms for neutralizing free radicals, unstable molecules that damage proteins, lipids, and DNA, accelerating aging and contributing to degenerative diseases. It also plays a role in converting the thyroid hormone T4, thyroxine, into its active form T3, triiodothyronine, which is essential for energy metabolism. In addition, studies suggest that selenium can modulate the immune system, protect against certain types of cancer, and influence fertility, particularly in men, where it is linked to sperm health. Despite its importance, the human body requires only trace amounts of selenium, usually measured in micrograms per day. Its deficiency, however, can cause serious disorders. One of the most well-known is Keshan disease, a type of cardiomyopathy that affects populations with low selenium intake, first observed in regions of China with selenium-deficient soils. It can also lead to hypothyroidism, lowered immunity, and reproductive difficulties. On the other hand, excess selenium, a condition called selenosis, causes symptoms like hair loss, brittle nails, skin lesions, fatigue, and neurological problems. Very high doses can be lethal. That's why selenium is often compared to mercury in terms of risk. What defines a remedy or a poison is only the dose. In the diet, selenium is found in Brazil nuts, fish, seafood, meats, eggs, mushrooms, and whole grains. The concentration in food depends directly on the selenium content of the soil where it was grown. This means entire populations may have different intake levels based solely on geography. Brazil nuts, for instance, are among the most concentrated natural sources on the planet. A single nut can contain more than the recommended daily dose. This peculiarity has sparked debates about supplementation and the dangers of dietary fads that promote excessive consumption of selenium-rich superfoods. In developed countries, excess is more common than deficiency. In mineral-poor regions, the opposite is true. Beyond human health, selenium also plays important roles in agriculture and industry. In small quantities, it is added to fertilizers to enrich deficient soils and improve the nutritional quality of crops. It is also used in the manufacture of glass, red pigments, and in solar cells and photocopiers, thanks to its electrical conductivity, which varies with light, a property known as photoconductivity. Even in minimal volumes, selenium leaves a profound mark on materials science, biochemistry, and technology. And like other elements with essential functions, its action is neither immediate nor visible. It is slow, constant, silent, but absolutely vital. Selenium reminds us that balance is the essence of life, that even the most modest elements play roles of profound and lasting impact. That health, longevity, and well-being do not rely solely on macrostructures, but on finely regulated atomic and molecular interactions. It is the invisible guardian of cells, the biochemical sentry of aging, and the sentinel of metabolism. And while it may lack brilliance, selenium shines where it matters most, in the invisible movement of life. With the symbol S and atomic number 16, sulfur is one of the oldest elements known and used by humanity, and at the same time, one of the most multifaceted. It has been associated with the smoke of hell and the cure of diseases, the fertility of soil, and the stench of swamps. Found in volcanoes, food, human proteins, and toxic gases, sulfur exists at extremes. It is essential for life, and yet can be highly lethal. From biblical and mythological times to modern laboratories, it has inspired both fascination and fear, respect and repulsion. But its importance goes far beyond the folkloric image of fire and brimstone. It is vital to biology, a silent protagonist in the chemical industry, and an unmistakable signature in the flavors, odors, and geological processes of the planet. Chemically, sulfur is a highly reactive non-metal that forms a wide variety of compounds, including sulfides, sulfates, and acids. Its most common elemental form is a bright yellow solid, naturally occurring in deposits near volcanic regions and hot springs. For centuries, it was extracted using rudimentary methods, but today it is primarily obtained as a byproduct of fossil fuel desulfurization. That's because sulfur is widely present in petroleum and coal, and its removal is essential to reduce the emission of sulfur dioxide, SO2, into the atmosphere, a gas responsible for acid rain and respiratory health problems. Thus, modern sulfur is partly a byproduct of humanity's attempt to mitigate its own environmental impact. In biology, sulfur is absolutely indispensable. It is present in two essential amino acids, cysteine and methionine, that make up structural and enzymatic proteins in all living organisms. Disulfide bonds formed between cysteine chains provide three-dimensional stability to many proteins, including hormones, enzymes, and antibodies. Sulfur is also found in B-complex vitamins, metabolic cofactors, and glutathione, a central antioxidant in cellular redox balance. Its role goes beyond structure. Sulfur actively participates in biochemical signaling, antioxidant defense, and detoxification of xenobiotics. Without it, cellular metabolism would collapse. In the world of flavor and aroma, sulfur is a true master of intensity. Sulfur-containing compounds are behind such distinct smells as garlic, onion, truffle, boiled eggs, and coffee. They are volatile, penetrating, and, in specific concentrations, either irresistibly pleasant or utterly repulsive. White wines, for example, contain traces of sulfur that influence their aroma. Natural methane gas is odorless, but mercaptans, sulfur compounds, are added to make leaks detectable. In fermented foods, aged cheeses, and rich sauces, sulfur compounds add complexity and depth. And at the same time, those same compounds are present in feces, sewage, and decaying animals. It is an element that spans the full range of human sensory experience, from pleasure to disgust, from cure to poison. In industrial contexts, sulfur has extensive applications. It is the raw material for producing sulfuric acid, H2SO4, one of the most manufactured chemicals in the world, and the foundation of the fertilizer, explosives, detergents, paper, petroleum refining, and mining industries. The amount of sulfuric acid consumed by a country is often used as an indirect indicator of its level of industrialization. In addition, sulfur is used in the vulcanization of rubber, a process that strengthens tires, as well as in pesticides, fungicides, cosmetics, and dermatological medicines. Its versatility spans from the laboratory to the field, from the industrial plant to the human body. Historically and symbolically, sulfur has always been linked to fire, transformation, and purification. Alchemists saw it as one of the fundamental principles of matter, representing the volatile soul, the burning spirit. In scriptures, it was associated with divine punishment, fire and brimstone being the metaphor for ruthless judgment. But with the advancement of chemistry, these mystical associations gave way to a broader and more accurate understanding. Sulfur is neither curse nor miracle, but an omnipresent participant in the cycles of nature and civilization. It is the link between fertile soil and animal protein, between volcanic smoke and the scent of garlic, between skin medication and mustard gas. Sulfur, therefore, is the chemical portrait of ambiguity. It burns, yet it heals. It stinks, yet it seasons. It destroys, yet it fertilizes. It dwells in the dark corners of matter and at the heart of living cells. It proves that what defines an element is not only its position on the table, but the context in which it manifests. And in the case of sulfur, that context is vast, dense, and astonishing, much like the planet we inhabit. With the symbol Cl and atomic number 17, chlorine is an element from the halogen family, a group of highly reactive nonmetals, and one of the most ambivalent substances ever handled by humans. In its gaseous state, yellow-green in color and sharply acrid in smell, chlorine is instantly recognizable to anyone who's been near a treated swimming pool, cleaning products, or certain laboratories. Yet behind that familiar scent lies one of the most aggressive and potent chemistries in the natural world. It is disinfectant and weapon, savior and poison, everyday and dangerous. Its history runs through the trenches of World War I, the halls of hospitals, water treatment stations, and environmental scandals. Chlorine perhaps best embodies the tension between beneficial use and destructive potential, and how thin and unstable the line between them can be. Discovered at the end of the 18th century by Carl Wilhelm Scheele, chlorine began its scientific journey as a gas, with curious oxidizing properties. Its name comes from the Greek chloros, meaning pale green, a reference to its vivid color. Over time, chemists realized that chlorine was an extraordinarily effective agent in destroying microorganisms. When it contacts water, it forms hypochlorous acid, which penetrates bacterial and viral membranes, oxidizing internal structures and leading to rapid cell death. This made it essential for purifying drinking water and treating sewage, interventions that alone eliminated outbreaks of cholera, typhoid, and dysentery in dozens of countries throughout the 20th century. Chlorine thus became an invisible hero of public health. In hospitals and homes, chlorine is one of the most common disinfectants. It's found in household bleach, cleaning products, surgical disinfectants, and industrial sterilizers. Its effectiveness is such that even a small concentration is enough to eliminate a broad range of pathogens, and yet it must be handled with care. Inhaled in large amounts, chlorine can cause severe lung damage, bronchospasms, chemical burns, and at higher concentrations, death. This toxicity was brutally exploited during World War I, when the German army released clouds of chlorine gas into enemy trenches, an event that marked the entry of chemistry into warfare and took thousands of lives by asphyxiation. Chlorine is also a cornerstone of modern chemical industry. It is used in the production of PVC, polyvinyl chloride, a plastic widely used in plumbing, electrical wiring, coatings, and packaging. It also plays a role in the manufacture of solvents, pesticides, dyes, medications, paper, and even certain pharmaceuticals. As a versatile reagent, it can chlorinate organic compounds and create molecules that resist degradation, a useful property in industrial materials but problematic for the environment. Chlorinated byproducts, such as dioxins and polychlorinated biphenyls, PCBs, are among the most persistent pollutants ever identified, capable of accumulating in living tissues and causing toxic effects even in minimal doses. Chlorine is thus also a source of deep ecological dilemmas. In treated water, chlorine's presence remains a topic of debate. On one hand, its antimicrobial action has saved millions of lives. On the other, chlorine reacts with organic matter in water and can form byproducts like trihalomethanes, which are potentially carcinogenic. Health regulations aim to strike a balance, disinfect effectively without compromising long-term safety. New technologies like ozonation and ultraviolet radiation have emerged as alternatives in some contexts, but none has fully replaced chlorine's robust, cheap, and efficient role. Chlorine has also been present in tragedies. Industrial leaks, such as in Bhopal, India, and accidents involving pressurized chlorine transport have caused mass casualties and severe environmental damage. Even on a small scale, the improper mixing of bleach with acids, a common household mistake, can release chlorine gas in bathrooms and kitchens, causing poisonings. That's why chlorine demands absolute respect. Its power is as great as its utility, and safety depends entirely on the knowledge and caution with which it is applied. Chlorine, therefore, symbolizes the dualities of progress: protection and risk, cleanliness and toxicity, life and death. It exists both in a bottle of disinfectant and in the pressurized canister of a battlefield. And perhaps its greatest lesson is this: that even the most valuable allies of civilization can become threats in the absence of discernment. In chemistry, nothing is absolutely good or evil. Everything depends on context, dose, and intention. And chlorine, with its pale color and intense presence, is the sharpest reminder of that truth. With the symbol Hg and atomic number 80, mercury is one of the most enigmatic and dangerous elements in the periodic table. Also known as quicksilver, it is the only metal that remains liquid at room temperature, flowing with a viscosity that makes it seem like an extraterrestrial substance. Its mirror-like metallic shine and fluid behavior have fascinated people since antiquity. Alchemists saw mercury as the essence of mutability, believing it to be the bridge between the physical and spiritual worlds, between base metals and the philosopher's gold. Centuries later, mercury became a scientific tool, marking temperatures, measuring pressure, forming part of vaccines and mirrors. But over time, the illusions faded and the dangers were revealed. Today, mercury is also a symbol of hidden toxicity, the invisible poison that accumulates in bodies and ecosystems, and the chemical responsibility that modern science cannot afford to ignore. The name Mercury comes from the Roman god of communication and travel, a nod to the metal's unique mobility. Its Latin name, hydrargyrum, means liquid silver, which explains its symbol, Hg. Mercury occurs naturally in ores such as cinnabar, mercury sulfide, a vividly red mineral used by ancient civilizations in paints and rituals. For centuries, mercury was used in mirrors, gold amalgamation, thermometers, barometers, and high-precision scientific instruments. Its ability to expand consistently with heat made it the ideal liquid for measuring temperature, which is why mercury thermometers were a global standard for generations. However, this same volatility that made it useful also made it dangerous. Mercury vapor is highly toxic, entering the lungs and accumulating in the brain, kidneys, and liver, where it causes neurological and degenerative damage. One of the most emblematic episodes of mercury poisoning occurred in the city of Minamata, Japan, between the 1950s and 1960s. The Chiso Corporation's factory was dumping methyl mercury, an even more toxic organic compound, into the local bay, contaminating fish and shellfish consumed by the population. The result was an outbreak of devastating neurological diseases, loss of motor coordination, blindness, paralysis, congenital deformities, and death. The so-called Minamata disease became a global landmark in the fight for environmental regulation and chemical safety. Since then, international agreements such as the Minamata Convention have aimed to limit the use and disposal of mercury, recognizing its universal risk to human health and aquatic ecosystems. In medicine, mercury was once considered an ally. Mercury-based compounds were used as antiseptics, laxatives, treatments for syphilis, and even as preservatives in vaccines. Thimerosal, an organic derivative, was used for decades as a preservative in multi-dose vaccines. Although studies show that thimerosal, in regulated doses, does not cause autism or neurological diseases, its presence generated controversy and misinformation, particularly in debates over childhood vaccination. Today, many countries have eliminated or reduced its use as a precautionary measure. In dentistry as well, mercury-containing amalgams were widely used in dental fillings, but they are now being progressively replaced by safer materials. The presence of mercury, even in microgram quantities, is now treated with extreme caution, and its removal is seen as a matter of public health. Despite restrictions, mercury is still used in certain specific areas. It remains essential in some scientific instruments, such as discharge lamps, standard electrodes, and precision analytical tools. It also continues to play a role in some industrial techniques, such as chlorine production via electrolysis, although alternatives are being developed and implemented. The main challenge remains the legacy. Mercury discarded in the past continues to circulate in the environment, especially in aquatic sediments and marine food chains. Predator fish, such as tuna and shark, accumulate methyl mercury at levels that can affect the human nervous system, especially in pregnant women and children. Mercury is therefore a mirror of the history of chemistry, from alchemical admiration to scientific caution. It is a metal that flows like water, but weighs like lead. It dazzles in form, but haunts in effect. It has taught us that brilliance does not ensure safety, that beauty can conceal danger, and that knowledge must walk hand in hand with precaution. It is one of the clearest examples of how an element, when misunderstood or misused, can leave lasting scars, and at the same time of how science can correct its course by confronting reality with honesty and rigor. At the farthest edge of the periodic table, beyond uranium, lies a silent, unstable, and often forgotten region, that of the synthetic elements. These are substances that do not occur naturally on Earth, artificially created by humans in particle accelerators, nuclear reactors, and ultra-secure laboratories. These elements, like einsteinium, fermium, livermorium, or oganesson, occupy the lower quadrants of the table, and despite their fleeting existence represent one of the greatest achievements of modern science, the ability to create atoms from nothing. With enigmatic symbols, extremely high atomic masses, and half-lives that last seconds, milliseconds, or less, synthetic elements are like atomic lightning bolts, brief, intense, but capable of illuminating human understanding of the very structure of matter. It all begins with the fusion of atomic nuclei. To create a synthetic element, scientists collide heavy atoms, such as calcium-48 or plutonium, with other stable nuclei, hoping that, for an instant, they will merge and form something entirely new. These collisions occur in highly controlled environments, like heavy ion accelerators, where magnetic fields guide the particles at near-light speeds. When the impact is successful, a new element is formed, but it usually disintegrates almost immediately, emitting alpha, beta, or gamma particles. Despite their brevity, these events are recorded with precision. Ultra-sensitive detectors analyze the radioactive signatures, confirm the creation of the new atom, and allow it to be named, often honoring cities, scientists, or institutions. Among the most famous synthetic elements is technetium, the first to be created in a laboratory, as previously discussed, which opened the gateway to this new frontier of chemistry. After it came dozens of others: neptunium, plutonium, americium, curium, berkelium, californium, and more. The so-called transuranic actinides, which follow uranium, were crucial in the nuclear era, both for energy and military purposes. Plutonium, for instance, is an essential component of nuclear weapons, but also powers reactors and space probes that generate electricity from the heat of its radioactive decay. Americium, on the other hand, is found in household smoke detectors, proving that even the most exotic artificial elements can have surprising practical uses. As elements become heavier, their stability decreases. Elements like ununoctium, now renamed oganesson, and livermorium exist for only a few milliseconds before decaying into smaller nuclei. They have no direct practical application, but help scientists study the so-called island of stability, a hypothetical region of the periodic table where superheavy elements might have longer half-lives and unique chemical properties. Discovering this island, if it exists, would be akin to finding a new atomic continent, a new type of matter, with properties we can't yet imagine. The search for these elements is more than scientific curiosity. It is a push to stretch the boundaries of what's possible in the construction of physical reality itself. From a philosophical perspective, synthetic elements represent a unique milestone in the history of science. For millennia, it was believed that the elements of nature were fixed, immutable, granted by some divine or natural principle. But in the 20th century, physicists and chemists showed that even this could be reshaped, that the fundamental blocks of matter could be rearranged, created and named, that humans armed with enough energy and technical precision could manufacture new atoms, and in doing so, rewrite the limits of the known universe. These elements then are testimonies of human ingenuity, of the patience of those who study events shorter than a blink, and of the ambition of those who dream of synthesizing what has never existed. Today, the study of synthetic elements continues in elite laboratories, such as the Joint Institute for Nuclear Research in Russia, the Lawrence Berkeley National Laboratory in the United States, and the GSI Helmholtz Center in Germany. Each new discovery is an international operation, with collaborations that cross continents and decades. The names given to these elements, like moscovium, tennessine, and oganesson, are tributes not just to places and people, but to the idea that science is a collective effort that transcends political borders. Though these elements aren't part of our daily lives, they bring us closer to deep questions. Is there a limit to the periodic table? Are there even heavier elements waiting to be born? And if they are born, what will they tell us about matter, energy, and the universe? Synthetic elements, though invisible to most people, are milestones of an ever-expanding frontier. They're not in the water we drink or the food we eat, but they lie at the threshold of human knowledge. They are made of collisions, of intent, and of nuclear secrets that last only a breath, and it is precisely for that reason that they fascinate, because they remind us that even the most unstable fragments can carry within them the force of a new scientific era. Far more than just a chart of elements, the periodic table is, in truth, a coded map of human development. Each cell, each atomic number, each symbol is a point of intersection between nature and culture, between the quantum physics of atoms and the historical destinies of humanity. It is not merely a logical arrangement of substances, it is the invisible backbone of everything around us, from the life pulsing within every cell to the concrete of our cities, from the glow of a screen to the combustion of a star. To look at the periodic table is, therefore, to look into a narrative that began in the depths of the universe and now unfolds in the hands of scientists, engineers, doctors, and artists. It is the hidden atlas of civilization, the elemental instruction manual of progress. Over the centuries, civilizations explored the elements long before their scientific names were known. Iron-shaped swords and empires. Copper ushered in the Bronze Age. Gold fueled religions, kingdoms, and greed. Salt was once used as currency and sparked wars. Gunpowder, made of sulfur, carbon, and nitrate, redrew borders. Every advancement in chemical science allowed humanity not only to identify the elements, but to isolate, purify, combine, and control them. The periodic table as we know it today was only made possible because, throughout history, we learned to listen to atoms and to extract from them energy, resilience, color, heat, and healing. It is the systematic record of the substances that sustain civilization, and at the same time, the blueprint for everything we have yet to build. Since Mendeleev proposed his first version in 1869, the periodic table has undergone radical transformations, incorporating both natural and synthetic elements, organizing patterns in physical and chemical properties, and revealing structures invisible to the naked eye. Its structure of groups and periods is not just aesthetic, it reflects deep laws of quantum mechanics, electron orbitals, ionization energies, and electronic configurations. Even to those unfamiliar with the language of chemistry, its rectangular, stepped and standardized form conveys a sense of order. And in that order lies one of science's greatest triumphs, the discovery that the universe is understandable, predictable, and classifiable. In this sense, the table is a graphic expression of human intelligence applied to the complexity of nature. But its power extends far beyond the laboratory. It reaches into medicine, engineering, food, communication, energy, and the arts. The calcium in bones, the phosphorus in DNA, the potassium in neurons, the iron in blood, the zinc in the immune system, all are living chapters of the periodic table residing in our bodies. The silicon in processors, the tungsten in industrial drills, the neon in lights, the lithium in batteries, the tantalum in smartphones, all support modern life. Cobalt treats tumors, uranium lights up cities, selenium protects against free radicals, lead, mercury, and arsenic remind us of the dangers of chemical imbalance. The periodic table is indeed the inventory of the foundations of life and risk. It is the vocabulary through which the planet speaks, and which humanity has decoded, element by element. Culturally, the periodic table has also become a symbol. It appears on t-shirts, posters, memes, and songs. It is celebrated as a masterpiece of scientific pedagogy, a teaching tool and a source of inspiration. Its beauty lies in its symmetry, but also in the density of meaning. Each element carries stories of discovery, accidents, revolutions, wars, scientific passions, and even betrayals. Some elements are named in honor of countries, scientists, laboratories, or mythologies. It is a gallery of scientific memory, where names like Curie, Einstein, fermium, and Mendelevium are immortalized not only for their contributions, but for the matter they inspired or discovered. The periodic table is therefore also a monument, not of stone or marble, but of symbols that transcend language, and it remains alive. New elements are still being created, even if they last only milliseconds. New applications continue to be discovered, even for substances once deemed useless. The periodic table is dynamic, evolving, open, like an ancient map still revealing unknown paths. Like a musical score where each element is a note, and civilization, a symphony in constant composition. It does not tell us only what is, but also what might be. Ultimately, the periodic table is the bridge between the micro and the macro, between the nucleus of an atom and the vastness of human culture. It shows us that understanding the world is often a matter of organizing the invisible, and that the key to the future may lie in something as small as an atomic number. It is more than science, it is the poetry of matter.